All right, consider the set of complex valued exponential functions like this, where the exponent is of the form of I and t, where n is an integer, t is a real number, and I is the imaginary unit. These exponential functions form an orthonormal basis in this sense. That is, if we take the inner product between two of these exponential functions, the value of this inner product is either 1 if n and m are equal, or 0 if m and n are different. Based on this fact, we can see that any Fourier series expandable function f can be expressed as a linear combination of this exponential function with the inner product between f and this exponential function as the coefficient. We can compare this with the case for the real vectors, where any vector x can be expanded as a linear combination of orthonormal basis vectors, where the coefficients are the inner product between the vector itself and the basis vector. So by comparing this, and this, we can say that the space or set of functions that are Fourier series expandable can be considered as a vector space with infinite dimensions. So let us first show this orthonormality. The inner product between e to the power of imt and e to the power of int, L2 inner product, is by definition 1 over 2 pi, integrate from 0 to 2 pi, and eimt and eint conjugate dt. So this is equal to, so the complex conjugate of this function is just, we negate the exponent, mt exponential of negative int dt. So combine these exponential functions together, we have eim minus nt. And we have seen before that this integral is equal to 1 if m and t are equal. That is, if the exponent is 0, then this is exponential of 0 is 1. So if we integrate this, we have 2 pi, and divide by 2 pi, we get 1. Otherwise, this becomes 0. So the result is the Kronecker delta m n, and we are done. Now, using this fact, we can show that the set of exponential functions, exponential of ijt, where j varies from negative n to positive n. So this set is linearly independent. So what do we mean by this being linearly independent? That means for any t that is real number, if we have the sum of this linear combination of this j from negative n to positive n, cj is a constant coefficient, and exponential of ijt, if this is equal to 0, then that implies, actually it's if and only if cj's are 0 for all j from negative n to positive n. So let's prove this. Actually, this direction is obvious because if all the coefficients are 0, of course the linear combination is 0, right? So we only prove this direction. Okay, so suppose this sum is equal to 0. Then multiply both sides by exponential of negative ikt, where k is an integer. So we have cj eijt times e negative I kt, which is equal to 0. Then we integrate both sides. So integrate both sides from 0 to 2 pi ijt e negative I kt dt is equal to 0. And let's divide both sides by 2 pi, and we still have this. But this part divided by 2 pi is the inner product. Cj inner product ijt ikt L2 inner product is equal to 0. And we know that this is Kronecker delta. It's not I, it's j. J delta jk equal to 0. But if we sum over j, then only one of j's, these j's, is equal to k. So that means ck is equal to 0. But k can be any integer between negative n to positive n. So therefore, all k from negative 1 to negative n to positive n, we have ck equal to 0. So all of the coefficients are 0 indeed. Now consider the Fourier series expansion of a function f of t, that is this, sum from negative infinity to positive infinity, and f hat of n, exponential of int, where f hat of n is given by this integral. F of t exponential of negative int dt. But this is nothing but the inner product between f and exponential of int, L2. So let's replace this f hat with this inner product, and we have the Fourier series expansion as this. F inner product int, lt, and exponential of int. Let's compare this with the real vector space. That is vector space x in Rn, and we can express this as x1, x2, and so on up to xn, and each of these are real numbers. Okay, and for this space we have this standard orthonormal basis set, that is Ej, where Ej is a vector consisting of 0, 0, 0, 1, 0, 0, 0, 0. Only the jth element is 1, everything else is 0. For this set, we have this orthonormality, Ei and Ej. If we take the inner product, that is equal to either 1 or 0. And it is 1 if and only if I and j are equal. Otherwise, it's 0. So for this, we had, so for the jth element of this vector x, xj, can be expressed as the inner product between the vector x and the basis vector Ej. So the vector x itself can be expressed as the sum, j from 1 to n, and the inner product between x and Ej and Ej. And this is very similar to what we just had here. So let's write it side by side. And from negative infinity to positive infinity, the inner product between f and the basis vector, exponential of int, int. So the vector x corresponds to the function f, and this inner product corresponds to this inner product, and this vector corresponds to this vector. So the structure of the n-dimensional vector space, real vector space, is very similar to the set of Fourier expandable functions. And in fact, the set of Fourier series expandable functions can be considered as a vector space with infinite dimensions in this sense. And noting that, this inner product represents the jth component element of the vector x. So we can say that this inner product may be regarded as the nth component of this function or vector. Now let's consider these two functions that are expressed as trigonometric polynomials, where the coefficients Cj and Dj are complex numbers. For these functions, we have the following. First, the norm of f is expressed as the sum of squares of the absolute value of the coefficients. So that's one. And second, the inner product between f and g is the sum of the product of the coefficients Cj and complex conjugate of Dj. And three, the absolute value of this thing, j from negative n to positive n, Cj Dj bar, is less than or equal to the sum of Cj absolute value squared, square root of it, and this negative n to positive n, Dj absolute value squared, and square root of this. Okay, let's show this. Actually, it's better to show the second one first, because the first one is a special case of the second one. If we just put f and f here, we have Cj and Cj bar, which is the square of the absolute value of Cj, so that we get the first one. So let's show the second one first. Okay, so f times g. So that according to the definition of the inner product, we have this f of t, g of t bar dt. And here by assumption we have f is this and g is this. So let's put them here. So j, cj, eij, t times, let's put k here, dk, eikt bar here. Of course, this bar means complex conjugate, so we have negative sign here and bar here. Here, the summation here over j and k, that they are both finite, so we can put them out of the integral. So let's put jk here and 1 over 2. Oh, wait a minute. So we can put these coefficients out. Cj dj bar and integral 2 pi ei j minus k t dt. And of course, this one integral is Kronecker delta. jkcj dk here, dk bar, and delta jk. So this is equal to cj dj bar. And we are done. And if we replace g with f, then f, this is equal to cj squared. And of course, this one is equal to the norm of f squared. So the first one has been shown, and the third one, this is just an alternative expression of the Cauchy-Schwarz inequality, right? Because the left-hand side is just the inner product between f and g, and the right-hand side is the product between the norm of f times the norm of g. So this is just a Cauchy-Schwarz inequality. Next, we show that we can define orthogonal projections for the set of functions that are complex valued with period of 2 pi. For an integer n greater than or equal to 1, we define the operator Sn, which operates on the function f, and that is defined as follows. That is sum j from negative n to positive n f hat of n, which is the Fourier coefficient of this function f, and times exponential of I j t. And of course, by the definition of the Fourier coefficient, we can also express this operator as this: the inner product between f and e to the power of ijt and e to the power of ijt. Okay, first, let us show that Sn is a linear operator. That is almost obvious from this expression. That let's say alpha is a complex number. Then if we apply Sn to alpha f, then that is expressed as alpha f times eijt, and by the property of the inner product, this is of course L2 inner product, we can put this alpha out of the inner product, and we can also put out alpha out of the summation. So we have this fijt eijt, but this is of course Sn applied to f. And so that's one thing. And suppose function g is of also complex valued and has a period of 2 pi, then this becomes f plus g here. And by the linearity of the inner product, we can split this into two inner products. ijt. And if we split this summation, and then we have s applied to f and s applied to g. So therefore this operator Sn is a linear operator. And the next property of Sn is this: Sn applied to f times g. If we take the inner product between these two, then that is equal to f times Sn applied to g. So the place of Sn doesn't matter, so they can be switched. Okay, let's show this. Let's take this left-hand side first. And we expand this Sn as this. So the inner product between f and exponential of ijt and exponential of ijt times g. Okay, so this part became this part. Okay, and then using the linearity of the inner product, we can take this summation and coefficient out of this inner product, this bracket. So that becomes j and f ijt and times bracket e exponential of ijt g L2. Okay, now let's swap the places here. Then we get the complex conjugate as f and e I j t L2 and g times ijt complex conjugate. Okay. Now let's put this constant inside this bracket on the second place. And we have f, and so if we put a complex number into the second place, then we take the complex conjugate of that number. So we already have this bar here, so we have double bar, which means we just take out, get rid of this bar here. So we have g eijt times exponential of ijt here, as this. Okay, and let's put this summation on to the second place because that is where j appears. Okay, so we have f and summation g eijt bracket closed ijt bracket closed. So this one is just a definition of Sn applied to G. So we are done. And finally, the third property is this. If we apply this operator twice to a function, then the effect is the same as applying it only once. In other words, this operator is idempotent. Okay, let's show this. So the left-hand side, first we expand this inside here. That becomes the sum of the inner product, eijt. Then we have shown that in the first part, this operator Sn is a linear operator. So we can take this summation and coefficient out of this operation, right? So therefore, this is equal to sum j f ijt outside, and then we apply Sn to this function. Then this becomes ijt. So if we apply this type of expansion again to this function, then we have, let's use k here, and so this function is exponential of ijt, and we have ikt here, ikt. But we know that this is orthonormal. So we have ijt here, and sum over k, Kronek's delta jk, akt here. So if we sum over this all k, everything except for k equal to j, this becomes 0. Otherwise it's 1, so we have ijt, and so all this summation becomes exponential of ijt, which is equal to Sn applied to f. And we are done. So let's review these three properties. First, we had Sn is linear. And we had this. We can swap the places of Sn in the inner product. And we also saw that Sn is idempotent. So we have these three properties. And now recall the projection operator we have studied for n-dimensional real vector space. So projection operator P applied to some vector x is defined as something like this. Let's say J is some subset of integers, let's say capital J, and then we take the inner product Ej and Ej. So this is a projection operator, and we saw that this P is linear, And if we apply this to x and then take the inner product with y, then that was equal to the inner product between x and py. And we also saw that if we apply projection operator twice, the effect is same as applying it only once. So these three properties are exactly identical. And we can say that this Sn is indeed a projection operator to a subspace of functions that are complex valued and with a period of 2 pi. As we've seen before, the space of functions can be considered as a vector space with infinite dimensions. And this projection operator Sn applied to F is something like this. J from negative n to positive n, ijt, eijt. So this projection operator projects the function on a subspace that is 2n plus 1 dimensional. So j varies from negative n to positive n. So there are 2n plus 1 terms in this sum. So this is a subspace. So for that matter, it doesn't have to be from negative n to positive n, but it can be any subset of integers. Okay, so we can define any projection operators in any subspace that is spanned by subset of these orthonormal basis vectors. Next, let's consider the difference between the function f and its projected version, Sn applied to f, L2 and squared. Of course, this is greater than or equal to 0, and let's expand this. So this is the inner product between f minus Snf with itself, and that is f norm minus 2 real part f Snf L2 and Snf norm squared. Okay, expanding this part, we have f sum j from negative n to positive n, f hat j exponential of ijt. And this one also, f hat ijt squared. Now, using the linearity, we can take this out and consider the inner product between f and this function. 2re and the sum j from negative n to positive n. Here, if we take the coefficient from the second place, then we have to make it complex conjugate, right? And Fijt L2. And here, as we have learned before, this is a trigonometric polynomial. So the norm square of this function should be the sum of square of the absolute value of the coefficients. So that is sum of j from negative n to positive n, absolute value of f hat j squared. And also notice that this part, this inner product is nothing but f hat j, right? So we have f hat j complex conjugate times f hat j. That is, so together, this becomes the absolute value of f hat j squared, which is real, right? So the real part, so this is naturally real, so we can just get rid of this real sign here. And this summation and this summation, they are the same, but we have negative 2 here, so after all, we have f norm squared minus sum of absolute value of f hat j squared. And now recall that we started from here. Okay, so this whole thing is greater than or equal to 0. That means this thing, the sum of square of f hat, absolute value of f hat, is less than or equal to the norm of f squared. And if this norm itself is finite, so if f norm is finite, then as n goes to infinity, this becomes equal to this. We have the Parseval's identity. That is the sum j from negative infinity to positive infinity, f hat j absolute value squared. This is equal to the norm of f squared. Let's see an application of Parseval's identity. Consider this function f of t that is equal to t between 0 and 2 pi, not including 2 pi. Considering this function as a periodic function with a period of 2 pi, we have seen before that its Fourier coefficients are as follows. So f hat of n is equal to pi if n is equal to 0. Otherwise, it's I over n. Now, the norm squared of this function is this 1 over 2 pi, integrate from 0 to 2 pi, and t squared dt. That is 1 over 2 pi and t cubed over 3. That is 8 pi cubed divided by 2 pi. That's 4 pi squared over 3. On the other hand, the sum of negative infinity to positive infinity, sum of the absolute value of the Fourier coefficient squared. So when n is equal to 0, it's pi. So we take this pi's out. Plus, and it's absolute value squared. So that means if we take the absolute value of this, and then that's 1 over n squared, so that's 1 over n squared. So, and that's symmetric around 0. So we have 2 times sum of n from 1 to infinity, 1 over n squared. So that's it. So according to Parseval's identity, this is equal to this. So 4 pi squared over 3 is equal to pi squared plus 2 times n from 1 to infinity, 1 over n squared. So therefore, let's see, so this one minus this one, we have 1 pi squared over 3. So pi squared over 6 is equal to the sum of 1 over n squared, n from 1 to infinity. So we have this identity involving pi and series. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.